Hello students, welcome to EPG Pathshala. I am Dr. Ajit Kumar Mahapatra from the Department of Physics and Astrophysics, University of Delhi, Delhi. Today we are going to discuss about the fluorescence quantum yield and lifetime under the paper titled Characterization of Materials 2. So students, let us see what we are going to learn in this module. The most important selection criteria for fluorophores in single molecule fluorescence spectroscopy will be discussed. Fluorescence quantum yield and lifetime will be discussed with examples. In introduction, the fluorescence and phosphorescence are observed when the molecules are excited by a powerful source of radiation. On contrary, chemiluminescence does not require a source of radiation where excitation takes place as a result of chemical energy produced from a chemical reaction. In fluorescence, the materials observe radiation and the electrons goes to an excited state, but the excited state is not stable and the electrons comes back to the ground state. Here the transition time is instantaneous. The light observed may be re-emitted almost instantaneously. In one or more steps, fluorescence is obtained when a molecule relaxes from the excited state to the ground state, and the fluorescence lifetime is of the order of 10 to the power minus 8 second and occurs at very shorter wavelength than the phosphorescence. Generally, the phosphorescence is obtained when a molecule relaxes from a transition state T1 to the ground state S0. The phosphorescence lifetime is in the range of 10 to the power minus 4 second to few second, and it occurs at a longer wavelength than the phosphorescence. The molecular phosphorescence spectroscopy has not been widely used as molecular fluorescence spectroscopy. This is mainly because phosphorescence is no more susceptible to radiationless deactivation mechanisms due to its relatively long lifetime. In addition, not so many applications on phosphorescence are available when compared to the fluorescence. Also, the phosphorescence signal is usually less than the fluorescence ones. For a molecule to show fluorescence, it should have some inherent properties. Those are: first, it should have a system with delocalized pi bonds in order to observe the light well. The second, it should be structurally rigid. Third, it should not have heavy atoms or paramagnetic atoms. And the fourth one, it should have preferentially be in solution, which is a high viscosity and contains no heavy atoms and oxygen free. A pi to pi star transition is the most convenient and useful transition in both fluorescence and phosphorescence. However, the N to pi star transitions promote the intersystem crossing and improve the phosphorescence. Excitations in a prerequisite step to emission Therefore, pi to pi star transitions are very important due to the following reasons. First, the major objectivity for the pi to pi star transition is high and allows good excitation. Second one, the energy required is moderate for less than dissociation energy. The third one is in presence of the most convenient solvent, which is water, the energy required to pi pi star transition. Fourth, the lifetime of the pi to pi transitions is rather short, which is around 10 to the power minus 7 to 10 to the power 9 seconds, which results in less collisional and radiation-less deactivation. So, generally, an emission spectrum is a mirror image of an excitation spectrum because they originate from opposite processes. The excitation spectrum more closely resembles an absorption spectrum because both originate from the same process of absorption of radiation by molecules. The emission spectrum is obtained at higher wavelength and is usually different from the excitation or absorption spectrum. This deviation from the mirror image is observed for transitions to excited states higher than the next excited state, such as S0 to S2 or S3. Fluorescence quantum yield. Both fluorescence quantum yield and lifetime are among the most important selection criteria for fluorophores in single molecule fluorescence spectroscopy. The fluorescence quantum yield, normally denoted as phi f, of a fluorophore is defined as the ratio of fluorescence photons emitted to the photons observed. The quantum yield can be described by two rate constants. First is the radiative rate constant, denoted as K subscript F, and the non-radiative rate constant K subscript I, comprising all possible competing deactivation paths such as internal conversion, intersystem crossing, or other intra and intermolecular quenching mechanisms. Mathematically, the quantum yield is calculated as phi f is equal to kf divided by kf plus sum over I ki. Even though complete prediction of the fluorescence quantum yield of a certain fluorophore is impossible, which would theoretically allow us to design fluorophores with ideal properties. Some requirements can be formulated for high fluorescence quantum yields. Those are: first, the fluorophore should exhibit a rigid structure to minimize radiation-less deactivation due to rotation or vibration of fluorophore side groups. Second, to ensure a low intersystem crossing rate constant, strong spin orbit coupling, for example, due to heavy atoms, should be avoided. And third, charge transfer transitions due to conjugated electron donor and acceptor groups, as for example in dyes often show bright fluorescence. However, there are many other non-radiative processes that can compete efficiently with the emission of light and thus reduce the fluorescence quantum yield. The reduction in fluorescence efficiency depends in complicated fashion on the molecular structure of the dye. The easiest way to determine the fluorescence quantum yield is the measurement of fluorescence efficiency relative to that of a standard solution. However, relative fluorescence quantum yield measurements are aggravated by many technical problems. Firstly, a fluorescence standard observing and emitting in the wavelength range of the dye to be investigated must be found. Unfortunately, only a few examples such as quinine sulfate where the phi F is equal to 70% in 0.1 N of H2SO4 solution, fluorescein that has phi F of 90% in 0.1 N aqueous sodium hydroxide solution, and rhodamine 6G has 10 rhodamine 101 whose phi F is 90 to 100% at concentrations below 10 to the power minus molar, which is 10 micromolar, have been characterized so far with high precision. Furthermore, as the measurements require comparison of the fluorescence efficiency of an unknown with a standard, careful attention must be given to corrections for differences in solvent temperature, the wavelength response of the monochromators and detectors, polarization effects, and so on. Fluorescence lifetime. The average time a molecule spends in its excited singlet state S1 before spontaneous emission occurs is denoted as fluorescence lifetime tau f. It can be expressed mathematically as tau f is equal to 1 divided by Ke plus sum over I Ki. The fluorescence lifetime of a fluorophore can be described as the decrease in the number of excited fluorophores n star bracketed T with time following optical excitations with a very short light pulse delta, and mathematically this process can be expressed as d n star bracketed T divided by dt is equal to minus k n star bracketed T plus f of t. The solution of this differential equation would be n star bracketed T is equal to n star bracketed 0 exponential of minus kt. Here k is equivalent to 10 to the power 8 second minus 1 as the number of excited fluorophores n star T is proportional to the fluorescence intensity IT. The integration between T is equal to 0 and at a time T is equal to T yields a single exponential function similar to a radioactive decay and is expressed as IT is equal to I0 exponential minus T by tau. That is, the fluorescence lifetime can be determined by measuring the time it takes the fluorescence intensity to reach at 1 divided by E of its original value I0 at t is equal to 0 upon optical excitation with a delta pulse. In the case of heterogeneous samples, due to different interaction possibilities between the biomolecule and the attached fluorescence level or mixtures of fluorophores, the fluorescence decay has to be described by a multi-exponential model. In principle, two popular methods for the determination of fluorescence lifetime exists: the pulse or photon counting and the phase modulation method. Instead of pulse excitation with Lyell pulses of duration substantially shorter than the fluorescence lifetime of the sample, the phase modulation method excites the sample with light whose intensity is modulated sinusoidally. The forced fluorescence emission of the sample directly follows the excitation modulations. Because of the finite fluorescence lifetime, emission modulation is delayed in phase by an angle relative to the excitation. In addition, fluorescence emission is demodulated due to the fact that the fluorescence quantum yield of common fluorophores phi f is less than 100%. Thus, fluorescence lifetime information can be extracted from both the degree of demodulation and the phase angle. However, as phase modulation methods are inoperative for fluorescence lifetime measurements at the single molecule level, the pulse method is mainly used. The pulse method, that is time correlated single photon counting, features high sensitivity, the ability to deal with low photon count rates with a time resolution down to the picosecond region, that is typical parameters to be handled in single molecule experiments. Quantum yield. The primary quantum yield phi is the number of photophysical or photochemical events that lead to primary products divided by the number of photons observed by the molecules in the same interval, or the radiation induced primary events divided by the rate of photoabsorption. Mathematically, phi can be expressed as number of events divided by number of photons observed, which is equal to the rate of the process, which is nu, the frequency, divided by the intensity I of light observed. The sum of primary quantum yields for all photophysical and photochemical events must be equal to 1. So, sum over I phi I is equal to 1. Common photophysical processes are the primary absorption, where we excite a light with energy h nu and the electron goes from a state S to state S star, and when it is in S star, the excited state absorption, this S star plus h nu will take the electron to the next excited state, which is S double star. So, other fluorescence emission, which is occurring due to the emission of electron from H star to come into the S or the ground state, at that time the equations reads like S star tends to S plus h nu, and the h nu is the energy of the light emitted. So, similarly, other photophysical processes are stimulated emission, intersystem crossing, phosphorescence emission, internal conversion, collision induced emission, collision deactivation are described in this table: branching ratio and quantum yield. The fraction of molecules undergoing fluorescence is equal to the rate of fluorescence divided by the rate of all processes. Thus, quantum yield can be expressed as a function of the rates of the competing decay processes. Here phi f is equal to kf divided by kf plus sum over ki, that can be written as kf at excited state S1 divided by kf plus KISC, which is the rate of non-radiative decay, plus the decay constant of non-radiative decay processes including intersystem crossing. So, this phi f is written as kf divided by kf plus KISC plus KIC plus all the rate of radiative decay processes or non-radiative decay processes. When a fluorophore absorbs a photon of light, an energetically excited state is formed. At this moment, depending upon the exact nature of the fluorophore and its surrounding, the end result is deactivating and return to the ground state. The main deactivation process includes fluorescence, internal conversion, and vibrational relaxation, intersystem crossing to the triplet multifold, and subsequent non-radiative deactivations. Let us have a look at the decay mechanisms of excited singlet and triplet states. During absorption, S plus H nu I is becoming S star, which is the excited state, and fluorescence S star goes to S plus H nu I by emitting the light of frequency nu I, and similarly internal conversion S star goes to S, and during that time nu IC, which is the frequency of internal conversion processes, is equal to KIC of S star, and during intersystem crossing S star goes to a triplet state T star. Here nu ISC is equal to K of ISC at S star. So, during all the processes, the rate of decay is equal to minus Kf at S star minus KIC at S star and plus minus KIC at S star. When the incident light is turned off, the excited state decays exponentially, and the quantum yield phi f can be written as 1 divided by Kf plus Kic plus Kisc. The fluorescence quantum yield phi f is the photon observed to photons emitted through fluorescence. In other words, quantum yield gives this probability of the excited state being deactivated by fluorescence rather than by another non-radiative mechanisms. If the incident light intensity is high and the observance of the sample is low, we may invoke the steady state approximation for the state S star, and that can be written as I absorption minus Kf minus Kic minus Kisc is equal to 0. Consequently, I absorption is equal to Kf plus Kisc plus Kisc. Here, the expression for the quantum yield of fluorescence becomes phi f is equal to mu f divided by I absorption, which is equal to Kf divided by Kf plus Kic plus Kisc. the efficiency with which a given photochemical process occurs is given by its quantum yield phi. Since many photochemical reactions are complex and may compete with unproductive energy loss, the quantum yield is usually specified for a particular event. Thus, we may define quantum yield as the number of moles of a stated reactant disappearing or the number of moles of a stated product produced. For Einstein of monochromatic light observed, where an Einstein is 1 mole of photons. Several secondary radical reactions then follow, making it difficult to assign a quantum yield to the primary reaction. Quantum yields for fluorescence that goes from S1 to S0 by emitting a light of energy h nu and intersystem crossing S1 to T0 for some aromatic hydrocarbons in ethanol solutions are expressed in this table. Here is an example for finding the phi values for different experimental processes. First example, let us take a sample of 4-heptane which was irradiated for 100 seconds with a 313 nanometer radiation with a power output of 50 watt. Under conditions of total absorption, it was found that 2.8 millimole of C2H4 was formed. What is the quantum yield for the formation of ethylene? The solution for this is, let us first calculate the number of photons generated in the interval of 100 seconds. Here the Planck's constant H is equal to 6.63 into 10 to the power minus 34 joule second, and the total number of photons could be calculated as power multiplied by the time of exposure divided by Hc by lambda, which is the values for the P delta T and lambda is taken from the question and solved for the determination of the value for n, which is equal to 7.87 into 10 to the power 21. Now the second step is to divide the amount of ethylene molecules formed by the amount of photons observed. Here the phi is equal to number of moles multiplied by the Avogadro's number divided by number of particles excited. So this can be written as phi is equal to n multiplied by Avogadro's number divided by n, and these values are given in the question, and that is 2.8 into 10 to the power minus 3 for the value of n, and we know the Avogadro's number is equal to 6.023 into 10 to the power 23, and the number of molecules we have calculated n is equal to 7.87 into 10 to the power 21. By putting all these values, the values for phi is calculated to be 0.21. The small values for phi indicate the presence of various radiative and non-radiative return pathways, and the primary photochemical reaction is the homolytic cleavage of a carbon-carbon bond. Let us discuss the quantum yield of a complex photochemical reaction. The overall quantum yield is the number of reactant molecules consumed per photon observed. For example, let us say hydrogen iodide, when we excite with light of energy h nu, the reaction looks like Hi plus H nu goes to H dot plus I dot, where this H dot and I dot are the excited states of the hydrogens. Those are not hydrogen atoms, but the excited states and the ions. When one of the hydrogen is now interacting with another Hi molecule, then this new Hi is going to have hydrogen H2 plus this I dot that is coming from the second molecule of Hi, and this I dot is mixing with the first I dot of the first molecule, and that goes to I2 plus the excited molecule. Here the overall quantum yield is 2, because the absorption of one photon destroys two reactant molecules of Hi. Therefore, in a chain reaction, the overall quantum yield can be very large. The fluorescence lifetime is the mean period for which an electron stays in the excited state before emitting a photon, and that can be written as star at time t is equal to star at time t is equal to 0 e to the power minus ke plus sum over ki. The lifetime is the inverse of the rate constant, which is written as tau f is equal to 1 divided by ke plus sum over I ki. If a population of fluorophores are excited, the lifetime is the time it takes for the number of excited molecules to decay to 1 divided by E times, or 36.8% of the original population. According to this, n star bracketed t divided by n star at time t is equal to 0, which is equal to e to the power minus t by tau. If there are no competing processes, then the fluorescence lifetime is equal to the true radiative lifetime and is expressed as tau f is equal to tau f 0 is equal to 1 by kf. But if there are competing processes, then tau f can be written as 1 divided by kf plus kic plus kic plus other rate constants for the non-radiative processes. Now let us discuss how to measure the fluorescence lifetime. So there are two ways for measuring the lifetime. First is the direct method, where the molecules are excited by very short pulse at t is equal to 0, and the decay of fluorescence intensity is then measured, usually by time correlated single photon counting. Here I t is equal to I at time t is equal to 0 exponential of minus t by tau. So the star of timing is equal to the star at time t is equal to 0 exponential of minus ke plus sum over I ki. The second method is the phase modulation method, which can be done in frequency domain. Here the excitation light is harmonically modulated with circular frequency omega, and so is the emission. Fluorescence lifetime can be deduced from the phase shift f and modulation m. Here the tau is equal to 1 by omega 10 phi, and the tau of modulation tau m is equal to 1 by omega square root of 1 divided by m square minus 1. So students, let us summarize what we have learned in this module. We have learned about the efficiency of fluorescence, which is an important difference between measuring absorption and fluorescence is the photoemission pathway, and that must complete with other energy decay pathways. This result is an efficiency of fluorescence and called the quantum yield phi, that can be written mathematically as h nu emitted divided by h nu observed. All the decay pathways that contribute to phi are sensitive to the environment of the fluorophore, including the solvent, the temperature, and the nearby electrons. The substances with the largest quantum yield approaching unity, such as rhodamine, displays the brightest emission. The lifetime is also important as it determines the time available for the fluorophore to interact with or diffuse in its environment, and hence the information available for its emission. The quantum yield and lifetime are the most important characteristics of a fluorophore. Thank you.